very straightforward, I guarantee you. I just want to know, do you understand the basic ideas and basic techniques that we've been using up to now? If you don't, then this is a good way to find that out, and then you need to reform yourself. So, for diagnostic purposes for you and for me, as much as anything else. So, people say, what's going to be on the exam? Well, the level of problems will be fairly similar to what you've seen on the OWL. Some of the problems on the assignments have been a little bit more difficult or have 7 parts or something like that. I'm not going to do that on the exam. It will be, each one is designed to test one particular thing. If I were you, what I would do is review the OWLs, maybe the homework assignments, and I would also sit down and think about what are the essential concepts and ideas for the course. In fact, let's summarize them right here. What do we have? We started with kinematics. The basic concepts in kinematics: position, velocity, acceleration. Velocity is the derivative of position. Acceleration is the derivative of velocity. Go in the other direction. Integrate. Velocity is the area under the acceleration curve. Position is the area under the velocity curve. The interrelations among those 3 concepts, of course, is very critical to the subject. Motion at constant acceleration. The most important thing about motion at constant acceleration is 1/2 AT squared. I guarantee you there will be a problem that involves using 1/2 AT squared on the exam. I haven't made it up yet, but I will certainly put a problem that involves that on there. Examples of motion at constant acceleration: we did free fall, the acceleration of gravity, g. By the way, I don't want you to get hung up in arithmetic on the exam. That's not the point. And therefore, if I have problems that involve g, I will probably say at the top, use g equals 10 for today. Now, if you happen to know g is equal to 9.8176542 or something like that, I don't care. More power to you, but don't use it on the exam. The exam will be designed to use on the assumption that you're using g equals 10. And I'm going to say that, if I do it this way, say that in big letters at the top. Please use g equals 10. If I tell you to, that's supposed to make life easier for you, not more difficult. So if you happen to know more accurate value, goody for you, but don't use it on the test. Free fall, let's see, projectile motion. Oh, and then 3D motion, vectors. Most important example of motion in 2 or 3 dimensions is centripetal acceleration for circular motion. V squared over R. I guarantee you there will be a problem involving V squared over R in there, because I think that's absolutely crucial. We've talked about kinematics. Can't think of anything else. Dynamics. Causes of motion, what we have here, Newton's laws in particular, F equals ma, and what we call free body diagrams. I guarantee you there'll be a free body diagram problem on there, set up Newton's second law and calculate the acceleration of something or other with various forces acting on it. So that will surely be an example where you have to apply Newton's second law of motion. Kinds of forces that we encountered: weight, mg. You ought to know the force of gravity on an object in this room is mg. You all know that, but that's something that'll probably be on there. Tension forces, normal forces, frictional forces, and the 2 kinds: mu static, less than or equal to mu static times the normal force, or equal to mu kinetic times the normal force. Possibly the force of a spring, F equals Kx, the force to extend a spring out a certain distance, although I kind of doubt it, that we haven't worked that much yet with spring, but possibly that would be it. Dynamics, what else can I say about dynamics? I think that's about it. Then we did work, power, energy. Work is force times distance. Certainly there would be a problem involving calculating work as force times distance. Of course, this became refined if they're not, the force and the displacement are not in the same direction as a dot product. And in general, it's F dot dr. I doubt there would be a problem in there calculating a heavy-duty integral to calculate the work, but there certainly would be some kind of a problem involving calculating work. Power is the rate at which work is done, dW by dt. Energy, the capacity to do work. We've encountered three types of mechanical energy. Kinetic energy, 1/2 mg squared. Gravitational energy, mgh. Spring energy, 1/2 kx squared. The capacity to do work. Compression or extension of the spring. And then, of course, well, the work energy theorem, perhaps. Conservation of energy, perhaps. Have I left anything out? Newton's law of universal gravitation, we did talk about that briefly, so perhaps I should put that in here under dynamics. So what I would be doing is, I say, I would work over the ALF, make sure that you know how to do all of the ALF problems and the problems on the assignment, at least to do problems of that general type. And then I would be making a list for myself. If there are any of these basic formulas that you find it impossible to remember, write them down on your cheat sheet and bring that in that one page of notes. I would put on there anything that I'm not dead sure I absolutely have committed to memory yet that's likely to show up on an exam like this, perhaps formulas for friction. That help? One last thing that I hate even to mention, but every once in a while in my lengthy career as a teacher, I've got burned for not saying something about this. Cheat. Especially for you in the front row, I'd like you to kind of move back and fill out the whole place. There's not really a whole lot of comfortable space here. But don't be packed tighter next to one another than you actually have to be. Because even if you're not doing it intentionally, it is pretty damn hard in an exam not to just inadvertently see that your neighbor had a different answer written down there than you did. And then you start wondering, he's kind of a smart fellow, maybe he's got it right. And then you find yourself changing your, don't let your eyes wander. And as far as conscious cheating is concerned, don't do it. We encourage you to work together on the OWLs, on the homework, I suppose in the labs, I don't know. In those contexts, I think it's great to work with other people, be talking about it and everything. That's an excellent way to learn physics. But on Friday, in the exam, that's not the rule of the game. The rule of the game on Friday is that I want to see your work and only your work. I hope that's obvious. But what may not be obvious to you, if you're even the least bit tempted, let me tell you a secret that you learn very quickly in teaching a class this size. The copy papers stick out like a sore thumb. Students have sometimes told me, well, so many people in the class, you can't possibly notice that my paper happened to be the same as somebody else's paper. You'd be astounded. I don't look for cheating on exams, but I have been amazed. I don't know what it is. You're reading 70 papers, and you come to some problem. Gee, that's a funny way to write the answer. It's correct, but it's a little bit strange. Hey, I saw that a moment ago. You dig back, and you stick the two papers next to each other. Wow! So, as I say, I'm not boasting about this, but it is amazing how much it sticks out like a sore thumb when papers are copied. So don't do it. Every once in a while, when I have encountered cheating, which thank got is very rare in my experience. But almost always when I confront the student with it, they say, you know, I'm terribly sorry, but I was desperate. I didn't have a chance to study for that exam. My girlfriend just left me or something or other, you know, and I was just desperate, so it was the only way I could go. If you're desperate, come and talk to me, okay? We can make accommodations for absolutely anything. I'm on your side. Up until the moment that copying occurred, in which case I switched sides completely, then no sympathy. I think it stinks. So, not that it matters to me, it's unfair to the other students, really, and it's nasty anyhow. So, don't do it. If you're desperate for some reason, please come and talk to me. We'll find some way to resolve the issue. But the worst thing in the world you can do is to copy. Then you just dig yourself into a much deeper hole. Enough of that nasty stuff. Go back to the good stuff. Energy. Last time I was talking about energy and the conservation of energy. Energy is the capacity to do work. Or more precisely, the amount of work that a system is capable of doing by virtue of some features of it. And there are many different forms that energy can take. We encountered several. Kinetic, 1/2 mv squared. That's the capacity to do work by virtue of motion. An object of mass m moving with speed v is capable of doing work for you as it comes to rest. And the amount of work it can do for you is exactly 1/2 mv squared. There's gravitational. That's the capacity to do work by virtue of height. If you lift an object up to a certain height h, it's capable of doing some work as it falls back to ground level. And the amount of work it can do is mgh. If you lifted it to. There's spring energy. That's the capacity of a spring that's compressed or extended to do work for you. How much work can it do? 1/2 k, where that's the constant in Hooke's law, the spring constant. Depends on the stiffness of the spring times x squared, where x is the amount that you compressed or extended it from its equilibrium position. By the way, an interesting feature of that formula, it doesn't matter whether you extend it out a distance x or shove it in a distance x. One of those would be positive and the other one negative, but it doesn't matter because you squared the x. So the amount of energy stored in a spring is the same if it's pulled out 2 centimeters as if it's squeezed in 2 centimeters. So there are various different forms of energy. Why is energy important to us? Basically because the law of conservation of energy, which says that you can convert energy from one form to another, as for example when you drop a rock, it was gravitational energy. When it hits the ground, it's kinetic energy. Or you can transfer it from one object to another, as in a collision, where one object has kinetic energy, it bounces off another one and transfers some of that kinetic energy to the other one. You can transfer it from one object to another, but you cannot create it or destroy it. That's the law of conservation of energy. The total energy is the same after any process as it was before the process. In that discussion last time, however, there's one kind of force that I did not mention, and for good reason. That's the force of friction. Here's the problem. Suppose that I got this brick here, and I give it a shove. At the beginning, just after I shoved it, it has some kinetic energy, right? 1/2 mv squared. No, it doesn't. That energy disappeared. Where did it go? You and I probably know, I do, and you probably know, where the energy went, the kinetic energy that was originally in that brick. Where did it go? It was converted into heat, thermal energy in the brick. If you took a thermometer and shoved it into that brick now, you'd find that that brick was a little bit hotter than it was before the temperature has gone up. And the energy that had been kinetic has been converted into thermal energy, heat. So energy was actually conserved in that process, but it was conserved in a kind of hidden way. Yeah?
Is the sound it makes considered heat?
No, sound would be a little bit of energy too. You're quite right. So there's a little bit of energy, what would we call it, acoustic energy that came out of that as it was scraping across there. Very good point. In fact, in practice, you would find that the amount of energy that was radiated away in the form of sound was minuscule compared to the amount that went into heat. Heat is the big dump in the case of friction. And other things like sound and light, maybe a tiny little piece, but once well taken. But the critical point is, whether it went into sound or went into heat, it had disappeared as far as mechanical energy is concerned. Mechanical energy, the obvious kinetic energy, gravitational energy, something having to do with the motion of the thing or the location of the thing, all of that is gone. That energy, from a mechanical point of view, has disappeared. Therefore, bad language, we say friction is a non-conservative force. Friction, kinetic friction, I should say kinetic friction, static friction is a different ballgame, but kinetic friction converts mechanical energy typically kinetic energy into non-mechanical form, heat, etc. If you want to include acoustic, etc. It converts it into other forms, and therefore we say that friction is non-conservative. Now, bad language, because non-conservative is you're supposed to think non-conservative doesn't obey conservation of energy. Of course it obeys conservation of energy. Everything obeys conservation of energy. But it doesn't obey conservation of mechanical energy, if you will. From a mechanical point of view, that energy has disappeared. Yeah.
Just in the past, when in physics class in high school, they always said that I believe the way we learned it was that the way they defined conservative versus non-conservative was whether it depended upon the path and
I'm coming to that.
How
is that consistent with it? I'm giving you the sort of casual definition of non-conservative here,
okay.
Or an example of a non-conservative force. That's the next order of business. It's precisely the question, how do I characterize a force? How do I know in advance whether a force is going to be conservative, the way that gravity is, for example, or non-conservative in the way that friction is? Friction is non-conservative, not in the sense that it doesn't obey the law of conservation of energy in the large sense, but it doesn't obey the law of conservation of mechanical energy, if you will, in the small sense. It converts mechanical energy into some other form, and therefore, if we're talking mechanics, it's casually, we'll say it's a non-conservative force. But question, how do I characterize non-conservative forces? And you put your finger on what the actual formal definition is. I'm coming to that in just a second. Where are we? We say friction is a non-conservative force, that bad language. Bad language, but we'll polish it up and you understand what it means for the moment. So I confront now a very subtle question. How do you distinguish conservative forces, ones that do obey the law of conservation of mechanical energy, such as the force of gravity or the force exerted by a spring? How do I distinguish those in a fundamental way from forces like friction that do not conserve mechanical energy? So, question, how do you characterize conservative forces? This, if you like was just a warning that not every force in nature actually satisfies the law of conservation of energy in its obvious superficial form of conservation of mechanical energy. So how do we characterize, on a deeper level, forces that do satisfy conservation of mechanical energy, and how do we distinguish them from those that don't? That's the issue. Now I'm going to run an example to begin with, and you're going to say, what on earth does that have to do with the question? I'll tie it back in a moment. So, example 1. Here's a force. F, the force acting on some object, is equal to, I'm just going to make one up, 2y I hat plus 3j hat. So, it points in the x direction. This component is in the x direction, and it gets bigger and bigger the larger y is. This component points in the y direction, and it's just counts as always 3. Now I'm going to ask you a peculiar question. Here's x, and here's y. And I propose to go from the origin, A, out to the point 2, 2. And I'm going to do that by 2 different routes. First, I'm going to go out by this route. We'll call that route 1. And then in a moment, I'm going to go out by this route. We'll call it route 2. That's from the point A out to the point B. And I want to know, how much work does it take No, I'll ask the question the other way around. How much work does F do when I move an object from point A to point B? You got the question? As I say, at this level, it probably sounds like a very peculiar question to be asking. But first of all, we'll do it by route 1. By route 1, that's where I go along to the point x equals 2, but still on the x-axis, and then I go up to point B. You ready? On that leg, this actually consists of 2 parts, so maybe I better label them. Part 1, when I'm going just along the x-axis, what is the displacement then? In general, remember, W is equal to the integral of F d dot dr, the dot product of the force and the displacement. So along this leg here, the displacement is purely in the x direction, right? It's just going in the x direction. This would be dx, and it goes in the points in the I hat direction. What happens when I take the dot product of F and dr? The dot product will pick out just the x component here, and I will get F dot dr is equal to 2y, the x component of F, times dx, the x component of dr. Did that make sense? This is a kind of subtle reasoning. Well, let's do it a different way. Remember that for work, it's force times distance, but only the force along the direction of motion counts. So along the direction of motion, that's the x direction here, so only this component counts. So it's 2y times the distance I went, dx. But folks, what is y on that particular leg? 0, right? Because I'm going along where y is equal to 0. But y equals 0, so this whole thing is equal to 0. Of course, on that leg or anywhere along the x-axis, y is 0, so the force points purely in the y direction, and no work is done if I go along purely in the x direction. So W is equal to 0 for that leg. How about the second leg now? dr, in this case, the displacement is purely in the y direction, right? I'm going up here now, so it would be dy in the y direction, and that tells me that F dot dr would pick out the y component of the force. This time is the y component times the y component. This is 3 times dy, and this time the work would be the integral of 3 dy. What limits, you tell me? What was y at the beginning of this leg? And what is it at the end of the leg? 2. So it goes from 0 to 2. This is 3 times the integral of dy from 0 to 2, which is just 2. The answer is 6. What was the total work done then to go from A to B via root 1? 0 plus 6 is 6. Okay, let's do it the other route now. I'm going to calculate the work done by that force if I move the object from the same point A to the same point B, but this time I'm going to go by that other route. If I go by route 2, again, it consists of 2 parts. Here's going up there, and that's then going across. On part 1, what's dr? You tell me. Follow what I'm doing? It's going straight up here, purely in the y direction, only y is changing. This would be dy, and it points in the j-hat direction, in the y direction. So if I calculated F dot dr along that leg, what would I get? The dot product picks out the y component of F, so it's just 3 dy. Actually, it's exactly the same as it was down here. So that says that the work done is equal to the integral of 3 dy from what limits? Starts at 0, goes to 2, 0 to 2. Again, this is 3 times 2 is 6. Now comes the punchline. If I go now along the top here, this time dr is again in the x direction. It's the x times j hat. F dot dr picks out the, I hat. It picks out the x component of F. That's 2y. Dx. This time, what is y along that leg? 2. Remember, this is like the one along here, but along here I didn't get anything because down there y was equal to 0. But up here, y is not equal to 0, it's 2. So this is equal to 4 dx, and therefore the work done is the integral of 4 dx evaluated between the limits x equals 0 and x equals 2. That's 4 times 2, or 8. How about that? What's the total work done to go from the origin out to the point B if I go by route 2? Then 14, huh? 6 plus 8, 14. That's not the same. Moral of the story? In general, done by some force is going to depend entirely on the path you took. Remember, I'm always taking the same beginning point and the same end point. But in general, for an arbitrary force, if you don't know something special about it, you should expect that the work done when I move an object from point A to point B is going to depend entirely on what route you took from point A to point B. The work done depends on the path taken. Is that surprising? I don't think so. I think that's actually kind of what you would have expected. You had to do a completely different sort of integral going along here and up than you did here and over, so it doesn't surprise me one bit that that gave you a different answer depending on which route you took. What is surprising, in fact kind of astonishing, is that there is a class of forces to which this force evidently does not belong, that have this special weird property that you're always going to get the same amount of work no matter which route you took between given beginning and end points. So, surprising? No. What is surprising astonishing, this is deep, is that there exists a class of forces I'll give you an example, although I'm not going to prove that it's the case. You could try doing exactly the same argument. If I just switch those around and make it 3I hat plus 2yj hat, 3I hat plus 2yj hat, if you use that one and did a calculation like this, you would come out surprising. Same answer, whichever route you took. And you say, well, that's just for those two routes. No, I don't care. You take this route here if you want to from A to B, you will come out with exactly the same answer. You pick two different endpoints, A and B, completely arbitrary endpoints, you're always going to get the same answer no matter how you calculate that work done. This kind of force has the property, the deep property, that the work done is independent of how you go from one point to the other. So what is surprising? There exist forces, there's an example, such that the work done is independent of the path. It is, of course, going to depend on the endpoints in general, but it doesn't depend on how you went from A to B. Have you got the criterion? So, we call forces of that type conservative forces. This is coming back to your definition, the one that you wanted me to give before, but that was just a warm-up for the official formal definition. I wanted to do this example in sort of gross detail so you understand exactly what it means to get a different answer for the work depending on the path you take. It's a very subtle business in my opinion. So, definition. A force is called conservative if it has that special property that the work it does going from A to B, any old A and any old B, is independent of the path taken. That's the secret criterion that I was looking for, that friction does not obey, but that gravity and springs do obey, that leads to the conservation of mechanical energy. The connection is by no means obvious at this point, but that's what I'm building up to. So far, a force is called conservative if the work it does going from A to B is the same for all paths. For instance, gravity is conservative in this sense. If I had, here's the vertical direction and horizontal direction, and I wanted to take some rock and carry it from point A here up to point B, I can tell you that the amount of work gravity does in going from A to B would be minus mgh, where h is this height here. And I don't care how you took the brick from one point to another. You could go straight across. How much work? Zero, right? Because the force of gravity would be downward, and you're going horizontally, so no work going that way. And then you lift the thing up here, the force of gravity is down, minus mg, and you're going up a distance h, so the work done by gravity is minus mgh. Or I could have gone by this route, straight up. How much work? Minus mgh. Along horizontally, how much work? Zero. Or I could have gone along a staircase in which I lifted a little bit and then slide it along to the right. Anytime I'm going horizontally, it costs me nothing. Every time I go vertically, I pick up a little contribution, but those vertical steps, when I've added them all up, is nothing but the height between here and here. So gravity has this property that no matter how you go from point A to point B, the force of gravity has done the same amount of work. All it depends on is what the net height you had to lift the thing from the beginning to the end was. So gravity is a conservative force. Springs. The ideal spring is also a conservative force. But friction kinetic friction is not. I already used the word non-conservative in the casual sense before for friction, just to describe the fact that it didn't conserve mechanical energy, that was converting mechanical energy into some kind of hidden form, mainly heat. But now in the formal definition, a force is conservative if the work it does going from A to B is the same for all paths. Is kinetic friction conservative in that sense? I say it is not. I plan to move this brick from that point A over to this point B. Certain amount of work that friction did, force times the distance. Now I do it by a different route. I'm getting there. Which route took more work? The second one, indeed. In fact, I could take a really circuitous route and do an unlimited amount of work in moving that brick from point A over to point B just by taking a long route. You know, the further I go, the more work friction force is done. So the work done by friction obviously depends on how you went from point A to point B. So, kinetic friction is not a conservative force in the formal sense. Gravity and spring forces are conservative. By the way, another way of thinking about conservative forces. Suppose that I got a conservative force and I carry the object around a closed loop and come right back to where I started from. So, some kind of a round trip that I come back to the beginning point. How much work would a conservative force have done? Zero, right? Because one way of getting from that point to that same point is not to move the thing at all, and then you certainly didn't do any work. So if it's conservative, the work done is independent of the path you took. It must be the case that if the thing goes around a closed loop and comes back to the beginning point, the total work must be zero. On the other hand, for a non-conservative force like friction, even though I bring this back to the same point, I've done a whole lot of work in bringing it back to the same point. So another way of stating the criterion, actually, is that for a closed loop, a round trip, the conservative force does no work. The non-conservative force, in general, does do some work. What's this good for? I'm going to introduce another definition and then play with it a little bit, and then we're ready to actually assemble everything and prove the law of conservation of energy to the extent that it's provable in classical mechanics. The next topic is potential energy. A word I've been scrupulously trying to avoid using up until now, although a lot of you I know are already familiar with it, so you've been using it back to me, but I've been trying to avoid it because I didn't want to introduce extra terminology until this point here. Potential energy. Suppose that I got myself a conservative force. Everything that I say now about potential energy does not work for a non-conservative force. There's no such thing as potential energy associated with friction, for example. It's nonsense for reasons you'll see in a moment. Given a conservative force, I define the potential energy at some point P, there it is, the amount of work I would have to do, not the amount of work that the force itself does, the amount of work I have to do to move the object in question from some standard reference point up to point P. So I've got some object and I want to know what is its potential energy at the point P. It's the work I would have to do to move the object in question from reference point, I'm going to call that O, to point P. So here's the reference point O. I'm going to talk about that in a moment. And what I do is move the object from point O up to the point P, and that's the potential energy of the object at point P. Now I'm going to make 4 comments on that definition. Well, let's first write it down, what this says formally. is that U, we'll use the letter U as the book does, for the potential energy at point P is equal to minus the integral from the reference point up to the point P of F dot dr. That's the work done in moving the object from O up to P. Comments? One. What's a minus sign doing there? I thought the work done was the integral of F dot dr. How come you slipped in a minus sign? Does anybody see what the reason for that is? Yeah.
Because as the work performed, the potential energy is only equal to, potential energy is equal to the work that it would take to get there.
Yeah. Precisely. You've got to listen to the fine print. The amount of work I must do to move it up there. I'm fighting against the force F. This is just like gravity. If I say how much work must I do to lift this brick up? The gravitational force is downward, mg. The force I exert is upward, mg. So their opposite force I had to exert is opposite to the force that the force itself was exerting. So here was the force itself, gravity or whatever. The work that I have to do fighting against that is minus F, is the force in question. I hate this minus sign. It was something that plagued me for the first several years that I was studying physics. Every time you're dealing with potential energy, there's that pesky minus sign in there, and I never could remember whether I'm supposed to put it in or I'm not. The question is, the point is that it's the work I do fighting against that force F. You could have defined potential energy as the work done by the force. Then your potential energy is minus everybody else's potential energy. You could do the rest of physics using your definition if you want, but there would be minus signs all over the place that would be incorrect. This is the customary way of defining it, and we're kind of stuck with that. So it's the work I do in fighting against the force F. Second comment, why did I insist that this has got to be a conservative force? Why must F be a conservative force? Does anybody see? If F were not, remember what conservative means. Conservative means that the work done going from any point A up to point B is independent of the path. So somebody else could have taken some different path, they would have got the same answer. Supposing that this force had not been conservative, then 6 different people trying to calculate the potential energy at P would come up with 6 different answers because they happen to choose 6 different routes. That's no good. That doesn't define anything at all. It would be a nonsense definition unless I had established before I even stated that definition that the work was independent of what route you took. Otherwise, it just doesn't define anything. A very subtle point. That's the definition in nonsense. It just doesn't define a function because it depends entirely on who's doing the job, what number they're going to get for that. How about the reference point? How do you choose the reference point? Answer, I don't care. Put it anywhere you want, just be consistent about it. There's a just like altitude. It sounds fishy, but it's really not. If I say to you that the altitude of Amherst is, I don't know what it is, 300 feet or something like that, you know that I'm secretly saying 300 feet above sea level, right? But that's just a convention. We know that you always measure height above sea level. You could have done it above the level of the Connecticut River if you wanted, or the bottom of some well in Hadley, I don't care. But what's physically important is how high Mount Holyoke is above Amherst. For that, I simply subtract the altitude at the top of Mount Holyoke from the altitude at Amherst. That number is going to be independent of what we used as our reference point, whether we use sea level or what. It's only differences of altitude that ever matter to us. So it doesn't matter what the reference point is, and that's the same story in potential energy. This is a lousy place to stop the story, but we got to stop. But yes, that's.